Alright, so after we did mapping, the next representation would be a table. A table is pretty much the same thing, just without all the little lines. A table has its place. Usually, whenever we start teaching with graphing, we always start off with a table. Usually, even in here, whenever you start, if you're struggling with graphing something, I always tell you to fall back on plotting points. Fill out a table. But a table just, has the ordered pairs in it. Okay, and it's been a little while since we talked about function. Function means that each x value is only used once. So is this a function? Yeah. So this one would be a function. Okay, a list just means that you have a grouping of ordered pairs. Gonna use this to kind of introduce set notation. Usually we just use these squiggly little brackets. There's a lot of different ways of doing set notation, but anytime you do set notation, it always starts with these squiggly little brackets. So okay, so is that a function or not? Yes, that's a function. Now, the problem with all of them that I've just done is it's a finite representation. A lot of times with functions, we have infinitely many ordered pairs represented. There's no way I can put infinite ordered pairs into a table or into a list. So then we have other representations, one of them being a graph. A graph, I can put an infinite number of ordered pairs in there. By making a solid line. And I put the little arrows on there to mean that it keeps going in that direction forever with no significant change. Okay, now we're not done with representations, but I'm going to take a little break right there to make sure you guys all know vertical line test. Vertical line test is the way that we can test graphs to make sure that they're functions. Now, we cannot have any repeating x values. So one way we can test to make sure we don't have any repeating x values is we take a vertical line and we draw a vertical line on my graph. That vertical line represents all the y values for that one x value. So for this one x value, it only has one y value. Now what we need to do in order to ensure this is a function is do that everywhere. Now, being intelligent people, we can look at this and tell that everywhere we draw this line, is this line ever going to cross that graph in more than one place? No. So by the vertical line test, this is a function. And I get lazy with my writing. So as soon as a vertical line, any vertical line, intersects a graph in more than one location, then it's not a function. So this is not a function. Sorry, I know I'm getting down to the bottom. That's why I'm trying to write all the way over to the right-hand side. And it only has to do that at one place. Because as soon as it does that, that means that that x value was moved or was used more than once. Which goes against our definition of a function. Okay, am I good to switch? All right, so last representation we're going to talk about is an equation. Again, this is another good way of representing infinitely many points. So yeah. So that would be a representation of a relation or a function. So not every equation has to be a function. For example, that one's not a function. Best way to tell that it's not a function usually is something is occurring to the y value. Yeah. Now, it's not an all the time case. It would be something that if you question it at all, you probably need to check it, which would mean that you plug in an x value and see if you can come up with more than one y value. So, for example, here, I could test it by, if I'm solving for y, I'm going to have to square root, right? So, let's see, if I plug in 8, I chose 8 because I know that 8 minus 4 is 4. So that's going to give me an easy square root. So it takes a little bit of forethought based on what is being done to the y. So whenever I square root, I get plus or minus 2. That means that I have these two ordered pairs. So this means it's not a function, because I have two ordered pairs with the same x value. Again, if nothing's being done to the y, if you just have a single y value, it's always going to be a function. You don't have to worry about it. What? If it's just a y, you're good. So, like this one, example 1, is it a function? Yes. Example 2, is it a function? No. Now, there could be I could give you examples that are a lot harder, but I don't believe on your homework they make it a whole lot more difficult than that. If they do, just, again, tomorrow, let me know and we can go over them. All right, so function notation. All right, function notation is this. F is the one used the most. I have no idea why, other than, it stands for a function. Function starts with F, so people like using F. It's f of x is how it's pronounced. Doesn't mean multiplication or anything like that. It means function of x. It means the exact same thing as y. You will see a lot in this class. Instead of ordered pairs looking like this, a lot of times you'll have ordered pairs that look like this. Just realize they mean the exact same thing. So we'll use function notation a little bit more than you have previously. You're not quite to the place where function notation is super helpful yet. In upper level math classes, function notation is really helpful because you want to manipulate functions without having to look at the equation constantly. So you will get to a point, if you continue with math, where function notation is very helpful, because you want to deal with functions without having to constantly write down the equation over and over and over and over again. Because the equation really doesn't matter half the time. All that matters is that you have a function. But again, you're not quite there yet. In order to start getting into that stuff, you have to start getting into calculus. Okay, So, biggest thing is realize whatever goes inside these parentheses replaces the x inside your equation. So the next set of examples is going to mainly focus on that. And that is my big push, is to get you guys to realize that. Okay, so I wrote out 3 functions along the top. We're going to practice with those. So if I do f of 5, what does f of 5 equal? 13. So I take the f function, and instead of putting x there, I replace that with 5. Okay, so g of negative 2. 4. Okay, h of 3, we talked about this a little bit on like the second or third day. This is a piecewise function. Piecewise functions, you take this number and you start on the right hand side. Where does 3 fit into these two inequalities? The top one or the bottom one? The top one. 3 is greater than 2, which says I'm going to plug 3 into this top equation. So I totally ignore the bottom equation. So that's 27 minus 3, so 24. Okay, we're good so far? Okay, so what's 6 going to be? That one always messes people up because I didn't actually give you an equation. 4. Okay, so negative 1 fits into this bottom one, right? What this says is anytime x is less than or equal to 2, then my function is equal to 4. Period. I don't need to plug my x value in, it's just equal to 4. So it's usually the easiest thing in the world, it's the hardest to understand because you really want to plug that number in. Okay, so now we get into the fun stuff. What's f of m? 2m plus 3. Nothing to solve. Can't do anything with it because this one has a variable, this one doesn't. Okay? So just to make my point, what's g of smiley face? Does it matter what I put inside those parentheses? Whatever I put inside those parentheses, you have to put in for x. So if I put n plus 1 inside the parentheses, before you start solving anything, we'll get to simplifying, but what does my initial equation look like? Okay? So I take out the x. Where the x was, I replace it with what was inside the parentheses. Now, this one you can simplify. Because this one I can distribute, and then I can add. I don't want you to see the last one, that's why I'm leaving it at the bottom. I'll move it up like this. Okay, so this one, I replace x. Now, this sometimes gives people a little bit of problem because I'm replacing x with an x, but that's okay. Whatever's inside the parentheses, I take out the x. Whatever's inside those parentheses, I put where the x was. Okay, now I square that. Remember, whenever I square it, that means I take it times itself. So it's not just x squared plus 4. I have to FOIL it. Okay, you want to try the last one by yourself? I don't know if you're ready for it. Especially the intricacies of my drawing ability. It's supposed to be a tree. I know, it looks like, a messed up baby hand. So g of tree minus triangle. So if you don't want to see, I'm going to write out the answer. If you don't want to see the answer, don't look back up. Oh, my drawing just keeps getting better and better the more I do it. Remember, x's and y's are just variables. Anything can be a variable. I can take my shoe off and it can be our next variable. Why not? You can sketch out my shoe and it can be your variable. You probably don't want that to happen. But anything can be variables. Don't get hung up on the fact that x has been your variable since you started Algebra 1. And also we get so hung up on things that anything can be a variable. It doesn't change the way algebra works. So that's why I want you to get with your function notation. Doesn't matter what's inside those parentheses, it replaces your x. All right, we good? All right, so let's move on from the craziness. You can tell your parents you drew trees in pre-calc today. And smiley faces. Don't forget the smiley faces. Those are always important. Okay, so we're going to go back to domain. I introduced it a while back. Remember, it's your independent variable, which for all intents and purposes is our x value normally. But you're going to be given functions. You're going to be asked what the domain is for those functions. Now, whenever you're asked what the domain is, that's usually a really difficult question. It's a lot easier to answer the question, what is not your domain? There's only really 2 times that your domain is really messed up most of the time. And that's with square roots and rational functions. Now, there are a lot of other cases where your domain is messed up. We're introducing these 2. There's other cases like logarithms and stuff, but we're pretending you have never been introduced to logarithms and tangent functions and those kind of things yet. So right now, we're pretending these are the only 2 things you've been introduced to. So those are the only 2 things that will mess up your domain. So, square root functions. When does a square root function not exist? Negative numbers. So, x cannot be less than 0, right? So, if x is greater than or equal to 0, we're good. If I'm going to use x, I should put an x in here. Okay. Rational functions. Out of all the x values, what is the one thing x cannot equal? 0. So what we're going to do is we're going to take those things and we're going to use those to figure out what the domain is. Because again, it's a lot easier to figure out what the domain is not and then use that to define our domain. So using this, that tells me that, so my domain is whenever x is greater than or equal to 0. And my domain is all real numbers. This is this fancy symbol for real numbers. Except for x cannot equal 0. For any other function that you're going to be given, your domain is all real numbers. So if they give you an equation for a line, it's all real numbers. If they give you an equation for a parabola, it's all real numbers. These are the only two you have to worry about. Okay, so if I take this one, the only thing I have to worry about is the square root cannot be less than or equal or less than 0. So what I'm going to do is I'm going to take what's inside that square root and say that that cannot be less than 0. Now I need to solve for x. So that means x cannot be less than 2. Now, this is an inequality, so make sure you follow all your rules for an inequality. So all your rules for normal math follow, except for what's the one time where you have to switch an inequality around?
Dividing by negative.
Dividing by a negative. If you multiply or divide by a negative, you'd have to flip that around. So my domain for this is x has to be greater than or equal to 2. Now, there are going to be some harder ones than that you're going to have to think about, but I want you to think about those before I just tell you how to do them. Okay, this one, x minus 5 cannot equal 0. So I solve that. And again, I know that you guys can just look at that and say, oh, well, x cannot equal 5. Again, I'm showing you the method for solving this because I'm showing you easy ones. They're not all going to be easy ones. So my domain is all real numbers except x cannot equal 5. If you have other ways of writing this, if another teacher has shown you in the past another way of writing that and you write it another way, I'm not going to get upset with you. You don't have to write it the way I show you how to write it. This is how I wrote it. There's ways of writing it in set notation where you do x is in the real numbers such that x does not equal 5. That's another way of writing it. I'm not requiring you to write it that way because I don't want to teach you new ways of writing things. I should write domain equals. But maybe you had a teacher in the past that required you to write things that way. I don't care. As long as you write something so that I understand you know what your domain is. All right, we good with that? I think we only got one more page. It's only been half an hour. All right, difference quotient. This is the one I'm excited about. This is calculus. Almost calculus. If you knew how to do limits, we could do calculus. If you knew how to do limits, this would be a derivative. Unfortunately, I'm not going to teach you how to do limits. Because that's like a whole chapter in calculus. Okay, but we can do difference quotients. This is like halfway there for doing a derivative. Okay. All you have to do is solve that. It's easy. All it is a really, really fancy function notation problem. Now, first of all, let me explain that there's lots of different versions of a difference quotient. This is one of them. Wherever you do it in your book, they're going to give you different versions. There's different ones like you might have x minus h on the bottom, and there's different ones. So don't think that this is the only form of the difference quotient. This is just one. I just picked one out of the book to give you. All right, so what I would suggest doing is starting off, instead of trying to plug everything in here at once, start off by finding f of x plus h. Because that's the part that most people mess up with. Okay, so what this means is I want to take every place where there's an x. So I'm going to take out all my x's. Every place where there was an x, I'm going to write x plus h. Now it just comes down to simplifying. Now remember, whenever I do this, x plus h squared means I have to FOIL that. Now, just to save time, I'm just going to jump to the answer of that. That was just me setting my marker down. That's nothing special there. Okay, so a big long mess. Okay, so now I'm going to put that into this. Okay, so I have, yeah. Yes, sorry. Thank you. Okay, so now I'm going to write that all into this. So here, maybe I should write that out. Okay, so there's f of x plus h minus f of x all divided by h. Now, you can do your subtraction of your function however you would like to. Some people like to distribute that negative sign inside there and change all their signs. That's fully up to you. You just have to make sure you subtract each thing. Be very careful about that. How do I get which? The minus f of x. So I put this in there, that's the green, minus f of x. So I just went back up and grabbed f of x again. Then all over h. Yes? You good? Okay. All right. What I like to do, since I'm just subtracting each of these out, I'm just going to go find each one of them and cross them out because I'm subtracting each one. So 4x squared minus 4x squared, that disappears. X minus x, that disappears. Negative 3 minus negative 3, that disappears. So what I'm left with is 8xh plus 4h squared plus h over h. Okay, this is the next part where a lot of people mess up on. So I'm going to do kind of an extra step here to try to help with this. So if you see how this works, I'm sorry I'm doing an extra step, but again, I'm trying to do this for you guys' benefit. Whenever you divide by something like this in a polynomial,